Okay, let's look at this question on the photoelectric effect from November 2018. It says to you, the threshold frequencies of cesium and potassium metals are given in the table below. Okay, so cesium's above, potassium's below. You can see that this value for potassium is higher than the value for cesium because 5,55 is bigger than 5,07, even if we're multiplying by 10 to the 14. It says define the term work function in words. So work function of a metal, it's the minimum energy needed to eject an electron from the metal surface. It says to you which one of the two metals in the table has the higher work function. Give a reason for the answer by referring to the information in the table. Remember that your work function is called WO and it's against H, it's equal to HFO. So this tells you that the work function is directly proportional to the threshold frequency. Okay, so the threshold frequency for potassium is greater than the threshold frequency for cesium, and as a result of this, potassium has the higher work function. Okay, and you can say because work function, I'm going to abbreviate to W0, is directly proportional to F0, and the work function for potassium is greater than the work function for calcium. This that I wrote over here, but write it in words, but we're going to run out of this space with this question. Now it shows you the simplified diagrams below show two circuits A and B containing photocells. The photocell in circuit A contains cesium and circuit B contains potassium. Ultraviolet light with the same intensity and wavelength of 5,5 times 10 to the negative 7 meters is incident on the metal plate in each of the photocells, and the ammeter in circuit A registers a current. By means of a calculation, determine whether the ammeter in circuit B will also register a current. Now there's a couple of ways to do this, but this is 3 marks, so let's look for the easiest way. In this question, they have given you the wavelength of the light, so they've given us lambda, okay? And we know for potassium, we know what is the threshold frequency. So we also know that this is electromagnetic radiation, so we can use this formula from the data sheet, this one here that says V equals F lambda. But the difference is, because this is electromagnetic radiation, it will be C equals F lambda. Remember the value for C, I haven't copied it down here, but C is 3 times 10 to the 8 meters per second. And the frequency we are trying to calculate, and we know the wavelength is 5,5 times 10 to the negative 7. So we can calculate this frequency of this light that's being shone on the metal plate, that is incident on the metal plate. If you put this into your calculator, you end up with 5,45 times 10 to the power of 14 hertz. Now if you go back to this question and you look at potassium's threshold frequency, it is actually greater. Okay, the threshold frequency for potassium is greater than 5,45 times 10 to the 14. So to answer the question, if the incident light has a frequency less than the threshold frequency, no electrons will be emitted, so the ammeter will not measure, the ammeter will not register a current. Okay, because we have not shone light with sufficient energy to emit an electron. Okay, now it says to you, calculate the maximum kinetic energy of an ejected electron in circuit A. So if we go back to my table here, it says to you, your energy of the total energy that you input is equal to the work function plus the EK max. So let's work it out. I'm not sure we're going to have enough space here. Okay, so we're going to copy the formula. The energy that we are inputting is equal to the work function plus the energy of the emitted electron, Ek max. So we know also from this data sheet that E equals HF. So we're going to substitute here immediately. 6,63 times 10 to the negative 34. Remember, this is Planck's constant over here, H, that I've just copied off the data sheet here. Okay, and then we want to go equals HF, but we can't do equals HF because we don't have F. We have lambda. But if you really wanted to, you could use this F that we calculated from the previous question. So pick one, either put equals HC over lambda. Remember, these two equations are what we're looking at over here. So E equals HC over lambda, 3 times 10 to the 8. If you do it this way, you will end up with a very accurate answer in your calculator if you can keep it in your calculator. Okay, and now look, I'm going to jump a step here. Do not be alarmed. I'm going to do some algebra. I'm going to flip this work function over to the other side and subtract it. Okay, so that I get the Ek max on its own. So this is going to be 6,63 times 10 to the negative 34. And my threshold frequency for the cesium in circuit A is this value over here. And I'm doing this shortcut because I'm running out of space. And this is going to be equal to my Ek max. Okay, so if you plug all of these numbers in your calculator, you should end up with something like 3,616 times 10 to the negative 19 subtract 3,36 times 10 to the negative 19 is going to be equal to Ek max. And then that means my Ek max, if you just work it out on your calculator, comes to 2,55 times 10 to the negative 20. It is energy. We have used SI units. We will be measuring it in joules, and energy is a scalar. Now it says to you, how will the maximum kinetic energy of the ejected electron, calculated in question 11.4 over here, change when the intensity of the incident light increases? Now remember, if you change the intensity, you do not change the Ek max. You only change how many electrons are ejected per second. So the Ek max is going to remain the same. Okay, the answer is remains the same.